Hello everyone. For our first video, we'll try to do something light. Before we move on to section 4.2, we're going to do the appendix, section 8.3, which is about polynomials, and hopefully it'll be a little more useful in the immediate future than what we actually covered in 4.1. Now, if you remember, our polynomials are just sums of powers of x with coefficients on them. All the way down to a1x plus a0. And if you remember, maybe from back in the day, we multiplied things. So we talked a little bit about factoring before, but let's say if I have a product, x minus 1, of two binomials, then when we want to multiply them together, often what comes to people's minds is we do this foiling operation. We try to match up the first two, outer two, inner two, and last two. So we end up multiplying 3x with x. We get 3x squared. Oh, not plus, but minus 3x plus 2x minus 2. And then we combine any like terms that we end up with at this step. But what probably wasn't shared when we were going over this is that what we're really doing is we're doing a lot of distribution. So we're going to do it again, except we're going to do a little bit of a safer way. And instead of trying some mnemonic, we're just going to utilize distribution. So distribution works as there is something on the outside of a set of parentheses, and it gets distributed to everything inside of the parentheses. So when I do it this way, I'll end up with 3x plus 2 multiplied by x minus 3x plus 2 times 1. I go ahead and stuck the minus out in front there. And then we perform distribution again on both of the remaining parts, giving us 3x squared plus 2x minus 3x. The 1 doesn't really change anything over here, plus 2. Sorry. You have to be very careful when you've got a minus sign in the middle, because the minus sign also distributes to everything just like the 1 does. So here I've added extra parentheses to make sure that I need to continue with my next step. So we've got 3x squared plus 2x minus 3x minus 2 at the very end, which matches what we got before. Now the reason I wanted to bring this up is because when we move on to section 4.2 with rational functions, often we're going to need to be, potentially often, we're going to need to be multiplying a bunch of polynomial parts and doing division for polynomial parts. So let's look at what we need to do when we have larger polynomials. Let's take an x plus 2 and multiply it by something larger, like x cubed plus 4x squared plus 2x plus 1. Now, there's too many parts here, so using a mnemonic like first, outer, inner, last doesn't really work. But what does work is I can take whichever piece I want. So I'm going to choose the largest part to be something which exists on the outside of the other set of parentheses. And so this large piece is going to be distributed to each of the smaller parts in our first set of parentheses. We'll end up with x times x cubed plus 4x squared plus 2x plus 1 plus 2 times x cubed plus 4x squared plus 2x plus 1. And I can redistribute all of these on the next step, giving me x to the fourth here, plus 4x cubed, plus 2x squared, plus x, and the second half, plus 2x cubed, plus 8x squared, plus 4x, plus 1. And then like before, we collect like terms. We've got x cubeds here, x squareds here, x's here, and the x to the fourth and the 1 just kind of stand alone. But what you may notice at this step, that all we've really done is we've taken each part of the first set of parentheses and eventually paired it up with each part in the second set of parentheses, which is one way you could do this, but it's a little bit safer to actually go through the distribution steps just in case when you're working through the pairings you don't accidentally skip over one. Now, on top of regular polynomial multiplication, it will be helpful to recognize some of the popular products or popular factoring rules that we're going to be faced with. If I have x plus a times x minus a, you can multiply this out, but you also may recognize this as the product that gives us a difference of squares. So this always works out to x squared minus a squared, which is not to be confused with if I have x minus a times x minus a. If I multiply those together, I'm going to end up with x squared minus 2ax plus a squared. You don't want to mix these up in any way because a square does not distribute across addition and subtraction. It means you have to split it up into a product of two binomials like that. Now if I flip it around and I instead look at x cubed minus a cubed, this has a special factoring form. I get x minus a multiplies to x squared plus ax plus a squared. And you can check that just by multiplying it out like we did on the previous page. We've also got one to match with the sum of cubes. So if x cubed plus a cubed, that actually factors out to x plus a here. And in the second part, we have the same parts, but we end up with a minus. So what really changes here is if I've got a minus sign, I'll have a minus, plus, plus. But if I have a plus sign, I'll end up with plus, minus, plus. Now the next thing we're going to want to talk about, and the last thing for this appendix, is going to be division of polynomials. Now we have a long division for numbers. Let's see if I take 104 and try to divide it by, say, 6. Well, then I look at how many times 6 can go into 10, say. There's 1. So that counts for 6. We have 4 left over. Bring the 4 down. Now we're looking for 6 into 44. Will give us 7. 7 times 6 is 42. We have 2 left over, and so we end up with the remainder of 2, which in numbers we'll deal with as a fraction. Polynomials work in a very similar way, but we have a little bit more requirement. So let's consider a simple one. Let's try x squared plus 4x plus 3. And we'll divide it by, say, x minus 2. Now, I've chosen these so that I shouldn't get a nice answer out of it. And we're definitely going to have a remainder. But one way we can check if whether or not we're going to get a remainder from a problem like this is x minus 2 as a factor would represent x equal to 2 as a solution. But if I plug in x equal to 2 into the larger piece, I'm definitely not going to get 0. So that tells me it's not a factor based on what we did in the previous class. Now what I want to look at is I look at the biggest parts. I want to make x squared out of an x. In order to make x squared from an x, I need to multiply it by x. And so I take x, multiply it by all of x minus 2, and I subtract it over here. So I'll have minus parentheses. X times x minus 2 is x squared minus 2x. We subtract these just by like terms, so we get 0 for the x squared terms, and we have plus 4 minus a negative 2, so that's a plus. We get plus 6x. Carry down our 3, and now we have to deal with 6x plus 3. And we match it up the same way. How do I get 6x from just the x? Well, I multiply it by 6. So I've got a plus 6 up there. And I essentially repeat my previous step. I take my 6, multiply it by x minus 2, and subtract it down here, just like we would with normal long division. So 6 times x minus 2 is 6x minus 12. So we get 0 there. And we have 3 plus 12, giving us 15 as the leftover. And I can't get 15 out of an x because I don't want to deal with any kind of weird fractional variable things, because I want to stay in the land of polynomials. So what this says is that x squared plus 4x plus 3 divided by x minus 2 is actually equal to x plus 6 plus a remainder of 15. And we write that as 15 over the x minus 2. Now when we get into the next and the following sections, this is going to represent what we call a slanted asymptote if we're trying to graph this previous part as a rational function. But we'll get there when we get there. We don't have to deal with it right now. Something to be aware of, though, is I've chosen an example with what I would call full polynomials. They contain all of the terms they possibly can. But sometimes we're missing terms. So let's consider 3x cubed plus 4x squared plus 7, and we want to divide it by x squared plus 1. Normally, you might want to set this up exactly the same way. You put the top under the little division box, and then you put the outside part outside. Sorry, the bottom part outside. But what we actually want to do with this is we want to fill in the little missing pieces. So instead of what I have written in blue, I'm going to work with what I have here in black. I'll take my 3x squared plus 4x squared, and I'm missing an x term, so I'll fill in a 0x plus 7. Now what I'm essentially doing is I'm filling in 0-digit placeholders, just like I would have in a number. Like if I have 101, I don't have any numbers in the tens place, so I put in a 0. And this x term counts just like a tens place would. And I'm going to do the same thing on the outside, just to be careful. And then I will proceed just like I did in the previous example. I look at the highest parts, and I say, how do I get 3x cubed from x squared? Well, I need to multiply it by 3x. and I take 3x times all of this, and I subtract it from my line. So I should get minus parentheses 3x times x squared, 3x cubed, 3x times 0x plus 0x squared. So notice how, because I filled this in, I'm pretty much guaranteeing myself that I'm not going to miss a line when I do my subtraction step, because I don't want to say my next part 3x and try to subtract it from 4x squared, because I might make a mistake there. So I'll have plus 3x here in my x column. Everything's nice and lined up, and I can do my subtraction. This part will be 0. 4 minus 0 is just 4. So we have 4x squared, and 0 minus 3x will give me minus 3x. And we'll go ahead and carry down the 7 now. And we repeat our process. How do I get 4x squared out of just x squared? Well, I only need to multiply it by 4. And 4 times all of this will give me 4x squared plus 4 times 0 is 0, plus 4 times 1. And I'll do my subtraction. 4 minus 4 is 0. Minus 3 minus 0 is minus 3. And 7 minus 4 is 3, plus 3. Now this division process is going to come in handy in a couple of sections because we have a factoring rule that we can do with large polynomials, but that's going to require polynomial long division, as well as some other work that we might not like. But we just have to stick with it because it's literally our only option. When we're looking for factors, or similarly looking for roots, they're pretty easy if we just have degree 1 or degree 2 polynomials, because degree 1 is just a line. We can find the x-intercept just by setting the y equal to 0 and solving for x. If we have degree 2, those are quadratics. We can use a quadratic formula to find the x-intercepts or roots. But for degree 3 or higher, there exist formulas for degree 3 and 4, but they are far from practical. And so our only recourse is going to be a method that's going to require us to try to use polynomial long division. So that's all we're going to have for now. The next video is going to be about 4.2, and we'll just continue on from the chapter from there.